Okay, so today we will actually finish off the course in the sense that there will be no new material after today. So a little bit of mop-up of Wi-Fi, and then talk about a very short and shallow introduction to network security, but at least some basic stuff, which is also part of the course. But before we get started, as you see, lecture on Monday, I decided to cancel that because, yeah, well, we don't have any new stuff that needs to be there, so maybe you can use this time to prepare a little bit for the exam or do some other useful stuff. And then final lecture on Thursday, when hopefully you had some time to look over the course. We will review it a little bit, and then I will be happy to answer all the questions you have. Perhaps not exactly what's on the exam, but otherwise anything related to the course I would be happy to clarify. So let's get started a little bit. Last time we talked about Wi-Fi, and so 802.11 Wi-Fi, specifies MAC and PHY, medium access control and physical layer, has many variations. So the most common medium access method here is called DCF, which stands for Distributed Coordinating Function, and uses CSMA with collision avoidance, CA at the end here. So essentially what it does, it listens for the medium under a specific time period called the diffs, and if it's idle, then we transmit. If it's busy, the completed frame what does it say here? Basically, if the medium is busy, okay, so let's just do it, we need to back off. Okay, so we need to wait until the medium becomes idle for a diffs, and after that we draw a random back-off time and start to count down the back-off. And the reason for this random back-off time is that there might be many stations who have sensed the medium when it's busy and are just waiting for it to become idle and transmit. So if we transmit directly, most likely we would have a collision, or it's a high probability of a collision. And since we can't do collision detection when we use wireless typically, then collisions are very costly. It takes a long time to recover from those. So instead we are a little bit more careful in accessing the medium. Regardless of this, there might be collisions, and to handle these collisions we have a simple sort of stop and wait type of protocol in Wi-Fi, where if we don't get an acknowledgement for the frame we just transmitted, then we know that something bad has happened, and then we back off and retransmit. And the reason why we handle these errors on, if you remember, for Ethernet, there is no retransmission protocol there in the Ethernet, and the reason for this is that there are few errors on Ethernet compared to on a wireless link. Okay, there are two ways to do carrier sensing, and one is what's known as physical carrier sensing, basically listening to the channel to see how much energy it's under, and if the energy is above a threshold, then we say the medium is busy. If the energy is or the received power is high enough, we can actually decode the frame that comes into the receiver, and in that frame we can read off the duration field in the frame, which basically says, okay, so this frame will take this and that many microseconds to be completed. And completed meaning transmission of the frame, waiting for an ifs, and then getting an ACK back, because that's the completion of the whole process. So this is called virtual carrier sensing, where we actually decode the frame and then set the timer until we can start to sense the channel again. And of course the channel is declared busy if either of these sensing methods is declared the medium as busy. Two big problems in CSMA with collision avoidance is hidden terminal problem and exposed terminal problem. hidden terminal means that a station that transmits is not necessarily heard by everyone. Okay. So if I'm far away from a transmitter, the receipt signal at my point might be low enough so I'm unable to detect that that transmission is ongoing. However, that transmission might reach the access point without any problems. Okay. And if I then start to transmit, my frame and the other station's frame might collide at the access point, and then most likely those frames are lost. Okay. So that's called the hidden terminal problem. So a station whose transmission is not detected when sensing the channel is called the hidden terminal. An exposed terminal is different. It's a station. So if I transmit a frame to my access point, there might be another station who hears my transmission, maybe in another room, and then backs off because it thinks that the channel is busy. However, that transmission from the other station might not interfere with my transmission to the degree that my frame is lost. And therefore, blocking that other transmitter is unnecessary. Okay? So it's unnecessary blocking of that station. And then we say that that station is exposed. Okay? It's blocked unnecessarily. And this is actually quite a problem in dense Wi-Fi deployments. So people are working on trying to mitigate this and mitigate the hidden terminal problem. And the hidden terminal problem, we can mitigate that to some degree by having small control frames before we actually transmit the long information frames. And these small control frames is clear request to send and a clear to send handshake with the access point before transmitting. Okay. We didn't talk much about physical layers, so let me just wrap that up. So in 802, we always have the link layer is LLC. Okay, so 802.1 is it right? Is LLC, and then below here we can have then different types of 802. 802.3, which is Ethernet, but in this case it's .11, right? And .11 has a yet another layer, sub-layer in the physical layer, which is called the Physical Layer Convergence Procedure, or PLCP, right? And the reason why we have one of these sub-layers here is that even though that the MAC frame is the same for all kinds of physical layers that we use, this one is used to somehow convert that into a suitable frame for the physical layer. So we'll see an example of this shortly. So if you're into acronym, there is a PDU on LLC layer, and that becomes the MAC layer service data unit, SDU. The MAC layer SDU puts on the MAC header and a CRC to protect the frame. This together then forms the Physical Layer Convergence Procedure Service Data Unit, or which happens also to be the MAC Layer Protocol Data Unit. And then we put on a preamble and a header in front of this. Okay, so 802.11 is designed to support LLC and then operate over many physical layers. So if you remember, we talked a little bit about the screenshot of my laptop a few years back. And here there was information about the network, the SSID, the type of security which is used on this. We briefly touched on that today. And then this basic service set ID, this is the MAC address of the access point I'm currently associated with. Channel 1 is specifying at what frequency band we are transmitting at the moment. So this is 2.4 gigahertz and it's 20 megahertz channel bandwidth. Country code here is for Sweden. And the reason for this, I'm not quite sure why this is important, except that I know that some channels are not available in certain regions. Okay, so it might be some type of, if this country code is wrong, that is, if I take this laptop to France, for instance, and I use that with a Swedish country code, there is a risk that I'm using a frequency which is not allowed in France, for instance. Okay, and the opposite. RSSI here is the receive power, so this is the RX power, and the noise here is the noise power, and these things together gives me the signal to noise ratio, and the signal to noise ratio determines what data rate I can use. Okay, so if this is high, the SNR is high, I can use a high data rate. If it's low, I can use a low data rate. And in this case, this SNR was sufficient to give me this 59 megabits per second. Okay, using a physical mode called 802.11n with a modulation encoding scheme index 6. So let's see what that means. First of all, it's OFDM. This I happen to know this. It was not clear from the screenshot before, but that's, I would say, always the case when it comes to the type of Wi-Fi that we are used to in our terminals and laptops. Okay, and this OFDM frame format looks something like this. Here we have the time axis along here, and frequency axis here. So frequency index 0 is the middle frequency of this frame, and so that happens to be at channel number 1. Is the center of channel number 1 is where we place 0, and then there is 10 megahertz to the left and 10 megahertz lower frequencies and 10 megahertz higher frequencies going this way. So the total thing here is roughly 20 megahertz. And then the next channel comes either below or above this.
Is 0 at 2.4 gigahertz?
Exactly, so this would be like 2.4 gigahertz roughly, right? It's not exactly at 2.4. One has to go into the table to see exactly where it's placed, right? So there is I think this was for channel number 1. Then there is channel 2, 3, 4, 5, 6, 7, and so forth. Not all of them are they are not 20 megahertz wide, which means that we cannot use channel 1 and channel 2 because they will overlap. So we need to space them with enough. I think 7 and 11 is yeah, there's some, I can't recall, but we cannot space them adjacent to each other. So 1 and 2 is not okay. So, but let's think of this as, oops, sorry. Let's think about 0 here as being 2.4 gigahertz, and then 26 here will be 2.4 gigahertz plus 10 megahertz, right? And minus 26 here will be 2.4 gigahertz minus 10 megahertz. Roughly, I mean, give or take a little bit, right? And then each rectangle here specifies a symbol, a QAM symbol. And the white part is empty, there is no power here. The blue part here is for synchronization, channel estimation, things like this. So the blue part doesn't carry any data. It's only there to for the receiver to synchronize, knowing that there is a frame coming in, and then specify where the frame is in the time frequency grid. Because the frequency, the local oscillator in the receiver is tuned to this frequency, okay, and that's the same as the transmitter local oscillator, but they are not exactly at the same place, right? So one has to synchronize the receiver in frequency. It has to change its local oscillator a little bit, so we line everything up. And then we also need to synchronize in time, so we line up where where's the beginning of a symbol, where's the end of it, when should we sample the match filter and all these things. So the blue parts here of the frame are for this. Then the yellow part here carries some information about what coding and modulation scheme is used for the data, and the data is in the green part here. So in this case, the information about the transmit mode and the modulation and coding index here is information about that is carried in the yellow part here. So the receiver doesn't know the format of the transmitted symbols. It doesn't know which QAM is used, what coding and modulation scheme is used. It has to read that off in the yellow part here. And the yellow part here is always transmitted with BPSK with a certain coding and modulation. So the yellow part can always be decoded. The transmitter the receiver knows how the data is encoded here. So it reads that off, and then it knows how to process the green part, and that's it. So the green part here might then carries these bits. Okay, the payload. While these parts here, the preamble and the header, is the blue part and the yellow part here. Okay, and just to give you a few numbers here, we said we had 20 megahertz channels, so the length of a symbol here is 4 microseconds. The spacing between subcarriers here, what is it? It's 20 megahertz divided by 52, so whatever that is. Okay, any questions on this? Okay, so this orthogonal frequency division multiplexing, as this is known, what it basically means is that we transmit a lot of QAM symbols in parallel over a frequency band here. So that's OFDM, and that's used in LTE and in 5G, so in 4G and 5G. It's also used a version of this in ADSL for wired transmissions. Okay, so these coding and modulation dependent parameters. So I said that the first part is using this coding and modulation. So this is for PLCP header information. It's always carried by this. But then which one we use for the green part for the data could vary from frame to frame, and that's SNR dependent. And it's not stated here, but the further down we go in the table here, the more SNR we need. Okay, and the further down we go in the table here, the more bits per, more data bits per OFDM symbol are we carrying. So, and for the ones which was on the screenshot on my laptop here, was modulation and coding index 6, which means 64 QAM, a certain channel correcting code, error correcting code with a rate 3/4. And here's a bunch of numbers that might not make a whole lot of sense now for you guys, except maybe, and I won't go through this, this is actually the data rate we get, 58.5 megabits per second for this one. So I could do better, right? I could have gotten 65, but I could also do much worse, 6.5 megabits per second. Okay, questions? Okay, so then let's go over to security here. So first of all, from a course perspective, when the course was created 5-6 years ago, security was not a part of the learning outcomes, but due to student feedback, we added that. People just basically wanted to know a little bit about this. So there is a learning outcomes for this, and the learning outcomes is to be able to explain the concept of symmetric and asymmetric cryptography and hash functions, and how these can be used to provide confidentiality, integrity, and authentication. So that's what we will talk about now. So this was new 2 academic years ago, so which means that there might not be a whole lot of this on all the exams, but I can almost guarantee it will be something on the exams to come around this, right? Because basically it's not part of the project, and therefore the only way to test this learning outcome is on the exam. So I would say security, as you know, right? There's hardly a single day without something in the news about security, data security one way or another. It's a very broad field, spanning from how one could protect old ladies for not using their bank ID in the wrong way and getting swindled, to how to protect transmission of bits over a particular channel, right? So it's very, very wide scope of this, super important. So we're only going to scratch the surface in this field here today. So I think it's worthwhile to take a course in this, because this is something, you know, one should know if one goes into this field. And also like this, I think when it comes to security, one should always leave that to the experts. Okay, you should never try to do security on your own, because then you're almost bound to fail. Many attempts have been done by amateurs, all of them have went badly, right? So there is solid methods for doing this, and one should use them, but one should know how to use them, and therefore one needs an expert on this. But it's good to know also from, as a non-expert, what one can expect and what one cannot expect. So with that saying, okay, computational security, I would say that most of the security we use today on the internet and also on, you know, cellular and whatever, is based on something called computational security. So when I say later on that something is impossible to do, what I really mean is that it's not possible with realistic computational resources. Okay? It might be possible to do in a theoretical sense, that there is an algorithm to solve this, but it will never be able to be computed within, say, the lifetime of the universe. And therefore we think of that as being impossible, right? So that's maybe not such a small step away from reality, but the thing is that when we want to protect ourselves against an adversary with some computational resources, we need to invest in a certain, say, length of the cryptographic keys that we use, which will introduce complexity both at the transmitter and receiver. So basically what we would like to do is we would like to provide enough security for our purposes, right? So what is enough security for our purposes? Well, it depends very much on the application, right? Say if it's military secrets, for instance, then those could be heavily protected compared to, say, I don't know, my Facebook feed or whatever, right? It's maybe not so crucial in comparison, okay? So there is always this cost and cost versus performance trade-off that needs to be done in all fields, including security. Okay, one thing from a theoretical point of view is that one should remember that computational security relies on the assumption that certain mathematical problems are hard to solve. Okay, and so it's not so easy to prove that something is difficult to do. It's easy to prove that something is easy to do. You just do it, right? You demonstrate an algorithm for doing this. But if you want to say, well, it's impossible to factor large products of two large primes. That's a difficult problem. That only means that today we don't know how to do that, and people have tried this, I guess, since the old Greeks to do this. So we have, I don't know, a couple of thousand years of experience saying that this seems to be difficult, but it doesn't mean that it will be, you know, maybe there is something there that we don't know about. Okay. We have good evidence for this, but it's still an assumption. So cryptographic schemes are constantly being analyzed for weaknesses. So every now and then one figures out that something, this is not so good, right? So last year, for instance, I don't know if you noticed this, but there was some weaknesses found in this WPA2, which is the security which is recommended for Wi-Fi at the moment. The first security protocol that was done for Wi-Fi was called WEP, so wireless or wired equivalent privacy, I think. It's completely broken, right? So it turned out to be a very poorly implemented security. So yeah. I told you earlier one should have experts doing this, and apparently they didn't use the right experts for this. So one should never use this when doing Wi-Fi. One should still use WPA2, right? Still the best we have. Okay. So what do we think about security? Well, the first thing one can think of is that we would like to keep communication between two parties, Alice and Bob, say, secret for everyone else. So this is the classical cryptography problem. So what we want to do is that we have two persons, computers or whatever, Alice and Bob, and they would like to communicate over a network where everyone can listen to what's going on in the network. And we want to still to make sure that Eve, the eavesdropper who's in the network here, is unable to figure out the message from Alice. Okay. So to introduce a little bit of terminology here, the data that we transmit is called the plain text. So it's M here. So think of this maybe as a text file or a video, whatever. It's a bunch of bits in this M. Could be a few bits, just one bit perhaps, or it could be millions of bits or billions of bits. Okay, so there are some bits here. And what Alice does is that before sending this, she runs an algorithm in her trusted environment to encrypt these bits using a key to do this. So the message and the key together forms what's known as the ciphertext, or C. So it's a function, it's an encoding function that has two inputs, the secret key and the message. And then you get another bunch of bits, C here, which is the ciphertext. The ciphertext is observed by Eve. Okay? So Eve knows C. And Eve would like to figure out M. I wonder if that's good or bad. Let's say that it's okay. Okay, so C is known to Eve here. But anyways, we would like to make it impossible for Eve to figure out what M is, even though she knows C. So Bob gets C, and Bob runs a decryption algorithm in his trusted environment. And the decryption algorithm here also have as an input this key K. So M here is the decoding of K and C. Okay. So think of the decoding algorithm as the inverse of the encoding algorithm. Now, the difference between Eve and Bob is that Bob knows the key. Okay. So as long as this key is generated and distributed in a secure way between Alice and Bob, that is sort of the setup. And what one would like to do then is to make sure that C doesn't carry any information about M if you don't know K. Okay. So again, Eve sees the ciphertext, knows exactly the algorithm for the encryption and decryption exactly, and could have the source code of it, right? The algorithms for this, but and knows everything about the scheme except the key. The key is the only secret here. So we don't have a secret encryption algorithm. We have a secret input to the algorithm, which is this key. So this is called Kerckhoffs's principle, and it's an old one from 1883. And it basically says this. It was phrased in another way, but a crypto system should be secure even if everything about the system except the key is public knowledge. So this is the principle. So here many homegrown security schemes is like, oh, I have a very clever algorithm here that I keep secret, and then my system is secure. But the problem with this is that once this is compromised, the whole system is broken, right? So why not have a system where the encryption algorithm and decryption algorithm is, is public knowledge, and the only thing that can be compromised is the key, and we can replace the key easily. Right? We just generate a new key if that ever happens. Right? Okay, so that's the general setup. Any questions on this? So let's do one scheme, which is actually a very good scheme, but it's not very practical. But it's a very good scheme, and it's called the one-time pad. And the idea here is that we generate let's make an assumption here. It's not very strong one, but suppose M is an n-bit sequence message. Okay, n could be any number. Then we generate the key K as a random n-bit pattern, okay, completely random, and this is shared between Alice and Bob, okay, the legitimate parties.
But how do you know that the key is just shared with Alice and Bob?
That's one of the problems here, right? But maybe Alice and Bob met and had a cup of coffee and exchanged the key and then moved apart and then used the key for communications. Another way to do this is that we have a courier that moves the key from one place to another.
So the key doesn't transmit?
No. You can't do that, right? So the problem here is that the key needs to be distributed, and that is actually as difficult as distributing the data from the beginning. But for instance, during the Cold War, there was a hotline from Washington to Moscow that was encrypted using a one-time pad. And essentially, this key was generated, printed out on computer paper, put in a briefcase, and somebody chained that to his or her hand and took the flight from Washington to Moscow. So that's one way to do it also. I mean, it's not super practical, but it can be done, right? Yeah, anyway, so once we have this key, the encryption is basically to take the XOR between the data bits and the key bits. And then the decryption is doing the same, taking the ciphertext and take the XOR with the keys. Okay, to see that this is correct, we take C here and replace that with M plus K. So it's M plus K plus K. And K plus K is equal to 1. And M plus 1 is, sorry, K plus K is 0, and M plus 0 is M. Okay. So then we're back. So the encryption and decryption is super simple. And this is secure if the key is never used. If you use it twice, then you can, there is an attack to figure out parts of the message. Okay. So to show this a little bit, why this is secure. Suppose that the message is some bits here, 0, 1, 0, 0, for instance. It's something. And then we randomly generate the key to encrypt this message. And we have to have a new key for every time we want to transmit the message. And maybe this is then 1101, say. And then the message, the ciphertext. So this is the plain text, this is the key, and this is the ciphertext. And the ciphertext is just the XOR here, bit by bit. So 0 plus 1 is 1, 1 plus 1 is 0, 0 plus 0 is 0, 0 plus 1 is 1. So my claim is that if this is chosen randomly, then in C, if we only know C, we know nothing about M. And one way to look at this is to think of this. Okay, so we typically think about information as something which is a random sequence of bits, right? So this one has a certain probability to be 0 or 1. It happens to be 0 in this case, and so forth, right? So that's what we did throughout the course. So this is drawn from some distribution. We don't know which one, but it's drawn from some distribution. We know that this is drawn from a distribution which is completely random. So this bit is 0 and 1 with probability 1/2. This is 0, 1 with probability 1/2, and so forth, right? Can we say something about the distribution of C here? In particular, let's calculate the probability that the first bit here is equal to, say, 1. So can we do this? Well, so the probability that C is equal to 1 is the probability that M1 plus K1 is equal to 1, right? And we can split this into two cases when this is true. It's when M1 is equal to 0 and K1 is equal to 1, plus the probability that M1 is equal to 1 and K1 is equal to 0. These are the two events that can lead to that C1 is equal to 0. C1 is equal to 1. Okay. And then looking at the first probability here, the joint probability that both that M1 is 0 and that K1 is equal to 1, let's write this as the conditional probability that K1 is equal to 1 given that M1 is equal to 0, multiply with the probability that M1 is equal to 0. So this is exactly the same. It's using Bayes' rule, going from a joint probability to conditional, multiply with the marginal probability of the thing that we condition on. Okay? And then we can write this also as the probability that K1 is equal to 0, given that M1 is equal to 1, times the probability that M1 is equal to 1, like this. Okay, now if we look at this joint, the conditional probability, what is the probability that K1 is equal to 1 when M1 happens to be 0? Okay, now we choose the key randomly without any relationship to the message that we want to encode. Okay, so the conditional probability here is simply the probability that we select, that we choose K1 to be equal to 1, which is 1/2. Same thing goes for this other conditional probability. This is just the probability that K1 is equal to 0, which is 1/2, like this. Okay, and now we're almost done. We continue here and say, okay, so this is 1/2 times the probability that M1 is equal to 0, plus 1/2 times the probability that M1 is equal to 1. And what is this? One half, exactly. Because we can write this as 1/2 times the probability that M1 is equal to 0 plus the probability that M1 is equal to 1, and the probability that it's either of the two possibilities is 1, so this is simply 1/2. Okay. So what we have deduced now is that the probability that the first bit in the ciphertext is equal to 1 is 1/2, regardless on how the distribution is for M1. You know, maybe it favors zeros more than ones or ones favor than 0. It doesn't matter. The probability that the first cipher bit is 1 is 1/2. And then, of course, it's symmetrical. So it's the same for the probability that the first bit of the ciphertext is 0. So with this, we can conclude that the ciphertext is completely random. If k is unknown. Okay. So if I don't know k, and I look at C, C just looks like a random sequence of bits. Carries no information about the M. Okay. So this means that impossible to say something about M from observing C. So I can let anybody look at the ciphertext, doesn't matter. They're unable to figure out what the message is. But if you know the key, it's super simple, right? You just take C, you add on K, modulo 2, and you get M. Okay, so if you have the key, that's it. Then you know exactly what's going on. If you don't have the key, you don't have a clue. Okay, so this one-time pad is very nice from this perspective, but then we also have this problem. Okay, we need a new key every time we need to encode a message. So suppose we have 2 gigabytes of data that we would like to encode, then we need 2 gigabytes of a key to encode this. And how should we transfer the key to between the recipients? Problem. So this is not super used in practice so much. But this is an example of what's known as symmetric cryptography. And symmetric means that Alice and Bob share the same key.
Is this the safest way to transmit secure messages?
This one?
Yes.
This is a perfect scheme. There is no better. There might be others, but there is nothing better than this. Assuming that you solve the key distribution problem. Yeah. So symmetric cryptography is sometimes also called private key cryptography. It's the same thing. And an example of a practical scheme which is used today is called AES, stands for Advanced Encryption Standard. And basically, there is no this one is pretty good, so there's no particular reason that I know of not using it if you use it for a new product. So it's the best we know today. Okay, so how about this? Let's take a break and then we go in to talk about asymmetric cryptography, where the transmitter and receiver have 2 different keys which are connected to each other. So that's the asymmetry of the thing. All right.